Friends, we have been studying scalars and vectors. I had briefly mentioned about scalar product and vector products of two vectors. Now here the question is, when we multiply one vector by one more vector, okay, the resultant can be a scalar or it can be a vector. So obviously when the product of two vectors is a scalar, it is called scalar product, and when the product of two vectors is third vector, then we call it a vector product. Okay, so now this scalar product, it is also called dot product, or then vector product is also called a cross product. Okay, so now when I have two vectors p bar and q bar, their scalar product is given by, it is written as p bar dot q bar, and when it is a vector product of these two vectors p bar and q bar, then that would be p bar cross q bar. Now one question here, scalar product of two vectors. When I have two vectors and if I am when I am multiplying one vector by the other vector, how can the resultant be a scalar product? But then for that you can take this example of work done. Now what is work done? Work done is work is said to be done when a force acts on a body and produces displacement in its own direction. Correct. Now obviously work done, it does not depend on the direction. It doesn't have any direction, right? It has got only magnitude. So though your component vectors are force and displacement, both are vectors, okay, but still their product, which is work, it is a scalar quantity. Another example can be power. It is the scalar product of force and velocity. Okay, now what about vector product or cross product? I have I can give an example of, let us say, torque. What is torque? Torque acting, torque, or it is moment of a force, or it is a turning effect of a force. I have this force acting on this body, okay, and this is fixed. This point O is fixed. This link can rotate. Now when this force F acts on this link, what happens? This link will rotate about this point O. Correct. Now what is the perpendicular distance between my line of action of force and then this fulcrum? I call this R. Okay. Then turning effect of this force, which we call torque, it is denoted by Greek alphabet tau. Okay. It is equal to R into F. Now here this R, okay, this is a vector and this is also a vector, so it is R bar cross F bar. Okay, we can have several such examples. You will be learning more in future. Okay, again, you have a vector quantity and it is multiplied by a scalar quantity. The resultant would be a vector. Example is momentum. Momentum is the product of mass and velocity of the moving object. Okay, so now let us try to learn more about the scalar and vector products. Now in this video we will be learning more about scalar product, and in the next video we will be dealing with this vector product in detail, right? So let us start with scalar product. I have two vectors p bar and q bar. Okay, the angle between directions of p bar and q bar is theta. Okay, theta is the angle. Then p bar dot q bar, the scalar product of p bar and q bar, that is given by p q cos theta. Now what is p and what is q? P is magnitude of p bar and q is magnitude of q bar. Correct, we are taking only the magnitude of these vectors, and then if theta is the angle, then the scalar product is given by pq cos theta. Now how do we really define the scalar product of two vectors? We define scalar product of two vectors as the product of magnitudes of both the vectors and cosine of the angle between them. So that is the formal definition of this scalar product. Okay, now this scalar product, it has got certain characteristics. We need to check whether this scalar product obeys certain conditions. Now what are these conditions? Okay, suppose I have mass of a body. Okay, it is, let us say, 1 kg, and velocity of that body is 3 meter per second. Correct. Then momentum, okay, magnitude of momentum would be given by 1 into 3. Correct. Now here there is nothing, no such thing as cos theta and all, right? So because you are multiplying a vector quantity by a scalar quantity, so the magnitude of the resultant is going to be simply the multiplication of magnitudes of these two. Correct. But then that doesn't happen with your scalar product. Now why is it so? Let us do that in detail. Basically, what is the logic behind having that cos theta? Okay, now suppose I have this vector p bar here, okay, and q bar is over here. Right, and what is the angle between them? Angle between them is theta. Okay, now as I said, p bar dot q bar is equal to pq cos theta. Okay, now can I write it like this? It is equal to p into q cos theta. Correct. Or can I write this as q into p cos theta? Now what is this? What is p into q cos theta and q into p cos theta? Okay, now obviously p is the magnitude of vector p bar, okay, and q is the magnitude of vector q bar. Okay, but then what I am doing here is p multiplied by q cos theta. What is q cos theta? Now from this point here, from the head of vector q bar, I'll draw a perpendicular here. Okay, let us call this point as O. Okay, OA and OB here. Okay, now what I'm going to do is I'm going to call this foot of perpendicular here as point C. Okay, now what is the length OC? In triangle OBC, what is my OC? I would say cos theta is equal to OC upon OB. Correct. And therefore I would say OC is equal to OB cos theta. Correct. And what is OB? OB is nothing but Q. So it is Q cos theta. Right. Now here you can if you put this Q cos theta over here, okay, so I could write this as P into OC. Okay, let us keep it as it is for the time being. Okay, let us see what is P cos theta. Okay, now what I am going to do is, again from this point O, I'll draw a perpendicular here. This was a perpendicular here, and I'm going to have this perpendicular. Okay, I'll call this point as point D. Okay, in triangle OAD, now what is cos theta here? cos theta would be adjacent side upon hypotenuse. Now for triangle OAD, OA is the hypotenuse, correct, and OD is the adjacent side. So cos theta would be OD upon OA. But then what is OA? Is it not magnitude of P bar, right? So it is OD upon P, correct? So I can say OD is equal to P cos theta, correct? See here, this Q cos theta I have substituted as OC here, okay, and now this P cos theta I'll be putting as OD, correct? Now what is OC and what is OD? Okay, OC is component of vector Q bar in the direction of vector P bar. In the direction of P bar, correct? What about OD there? OD is the component of P bar in the direction of P bar, correct? Component of P bar in the direction of Q bar, sorry. Okay, now so that means when we define the scalar product of these two vectors P bar and Q bar, I would say it is the product of magnitude of the first vector and component of the second vector in the direction of the first vector, that is one, or otherwise it is the this would be, I made a mistake here, it should have been Q, correct, or otherwise it is the product of the second vector and the component of the first vector in the direction of second vector. Okay, so that is the that is how we define dot product of these two vectors P bar and Q bar. Okay, now alright, so that was about definition, but then there are few laws, few mathematical conditions, like whether this scalar product is commutative or whether it is associative, correct? Now here you can see that we can very well say, now see, since it is a scalar product, it will be commutative. Okay, so it's like when I'm dealing with two vectors m and n is also equal to n multiplied, so m multiplied by n is equal to n multiplied by m. Okay, so my scalar product is commutative. Okay, you can reverse the orders, absolutely no problem with that. Okay, what about this scalar products being associative? Okay, now what do you mean by some product being associative? Suppose I have a vector a bar, okay, and dot product of that with a vector which in itself is a combination of two other vectors. Okay, for example, b bar plus c bar. So dot product of a bar with the resultant of b bar and c bar, that we can call it as a bar dot b bar plus a bar dot c bar. So this was the first one was definition, the second one is this. Rather this would be third one, the second one was the vector products, the scalar product being commutative. Now here we are proving that it is associative. Okay, number 4 I would say here, we have defined p bar dot q bar as p q cos theta. Okay, now cos theta is always less than 1, correct? So but then what is the value of theta here? Theta can be anything between 0 and 180 degrees. Okay, so if theta is equal to 0, 0 degree, let us say, then cos theta is equal to 1. Correct. Then P bar dot Q bar will be equal to P into Q into 1, which is equal to PQ. Correct. So it would be simply the product of magnitudes of the two vectors. That means when two vectors, they act along the same line of action, or when they act parallelly, okay, their product will be, the scalar product will be equal to product of individual magnitudes of the two vectors. Okay, but if theta is equal to 90 degree, cos of 90 degree is equal to 0. Correct. So my P bar dot Q bar would be equal to, P bar dot Q bar would be equal to 0. Correct. So irrespective of the individual magnitudes of two vectors, if they act perpendicular to each other, then the scalar product of these two vectors would be equal to 0. Okay. Now what if my theta is equal to 180 degree? When theta is 180, see, cos of 0 is equal to 1. Cos of 180 is equal to minus 1. Okay, cos of 180 would be equal to minus 1. Correct. Then P bar slash P bar dot Q bar would be equal to PQ into minus 1. So that would be equal to minus PQ. Now you can note here that we have this negative sign here that gives only negative magnitude of that sign. It doesn't have anything to do with the direction. Okay. Now for this, okay, I think I should give you an example of this two vectors, which are anti-parallel. Okay, they act along the same line but in opposite directions. Now one example of this can be a ball. If you throw a ball vertically upwards, okay, then the, see, acceleration due to gravity is acting downwards. Correct. The ball is moving upwards. Correct. So gravitational force is acting downwards and the ball is moving upwards. It is going against the gravitational force acting on it. Correct. So that means over there the scalar product of force and its displacement is upward, force is acting downwards, then the work done by the gravitational force of attraction acting on the ball would be negative, because the angle between the force which is acting downwards and the displacement which is acting upwards, that angle is 180 degree. Okay, so the work done over there would be equal to negative, or it would be equal to minus of mg into displacement. You can say, you can call it h, or height up to which the ball reaches, right? So that was about these three cases here. Okay. All right. Suppose let us consider this case. Okay. The vectors are acting along the same line of action, even the direction is same. Okay, but again, if magnitude of P bar is equal to magnitude of Q bar is equal to P is equal to Q, okay, then what would this be? Then P bar dot Q bar would be equal to P square, or you can call it even Q square. Correct, since the magnitudes are same. Okay, now let us go one step further. Okay, see, P bar and Q bar are acting along the same line of action, they are acting along the same direction, and if magnitude of both the vectors is equal to 1, so we are talking about unit vector. What is a unit vector? Unit vector is a vector acting in a particular direction and it has got magnitude equal to 1 unit. Correct, that is called unit vector. So if P bar, magnitude of P bar is equal to 1 and magnitude of Q bar also is equal to 1, then P bar dot Q bar will be equal to 1. Correct. And now here we are having we are having both the vectors acting in the same direction. Okay, but again, if I have unit vectors, if I have two unit vectors, but then they are acting perpendicular to each other, then their dot product would be equal to 0. Correct? Now let me explain this in little more details. Okay, now when we talk about unit vectors, you might recollect we had considered, some unit vectors along the coordinate axis. Okay, now I have my x axis here in this direction, I have y axis in this direction, and then z axis. So these three axes, x, y and z, they are mutually perpendicular. I call this unit vector along x axis as I cap. Now why cap? When I have cap above some vector, okay, that means it has got a magnitude equal to 1 unit. Okay, so I cap is a unit vector along x axis, j cap is unit vector along y axis, and k cap is unit vector along z axis. Correct? Now here, if you take I cap dot I cap, correct, so that would be equal to magnitude of I cap into magnitude of I cap into cos of 0 degree. Correct? Definition of scalar product. But then magnitude of I cap is equal to 1, so it is 1 into 1 into 1, so that is equal to 1. Correct? So similarly, j cap dot j cap would be equal to 1, and that would be also equal to k cap dot k cap. Correct? Now what? I want to find what is I cap dot j cap. Now see, this your x, y and z axis, they are mutually perpendicular. So angle between my x axis and y axis, it is 90 degree. So my I cap dot j cap would be equal to 0, and that would also be equal to j cap dot k cap, and that would be equal to k cap dot I cap. Correct? So I have this. This is one important thing which is going to help us in the for establishing something in the next video. Okay, so that is about this. Now again, I had said that in the while defining the scalar product, I had said that scalar product of two vectors is defined as the product of magnitudes of both the vectors multiplied by cosine of the angle between them. Okay, I also said that my vector product, the scalar product, okay, scalar product is commutative. That means p bar dot q bar is also equal to q bar dot p bar. Okay, let me explain that in detail. I am going to take example of work done by a force. Okay, now what is work done by a force? Work is said to be done when a force acts on a body and produces an acceleration in its own direction. Correct? So if I have this surface and I have one mass here m and one force F acts on it. Okay, now because of action of this force, the mass moves through a distance s along this surface. The mass slides, this initial position was A and now it has reached B. Okay, I want to find the work done by this force F. Okay, so what is my definition of work done? Work done is the scalar product of force and displacement. That is what I say. Okay, but then let us prove that how it really happens. Work done is equal to force multiplied by displacement, that is S. Okay, and I say that it is F bar dot S bar. Okay, but I don't know so far, you know, I'm just saying that work done is a scalar product, but then I really need to prove it. Okay, how do I do that? Now you see here, is the force acting along the horizontal? No, it is acting at an angle. And what is the angle made by this force with the horizontal here? This angle is theta, correct? And how did I define work? I said work is said to be done when a force acts on a body and produces a displacement in its own direction. Now just see here, this force is acting at an angle, correct? Is the displacement happening along the direction of force? No. Displacement is not happening in the direction of force, but then it is happening in the horizontal direction, correct? So obviously I would need to consider the component of force acting along the horizontal, correct? And what is that component? This is my F cos theta, and the other component is F sin theta, correct? This F cos theta is producing this displacement. We agree to that. Okay, what is this component F sin theta doing? Is it causing any displacement in its own direction? Is there any displacement in the vertical direction? No. So my work done is equal to F cos theta multiplied by displacement, correct? Displacement is S in the horizontal direction, so it is F into S into cos theta. This is number 1. Okay, how did we define scalar product? It is the product of magnitudes of both the vectors and cosine of the angle between them. Alright, now let us have the same scenario here. This is my displacement S bar, okay, and this is my force acting here, correct? This is my F bar. You know what, I'll take this component of F along this direction, correct? So this, if this angle is theta, then let us call this point, okay, I'll call this point O, point A, B, point C here, correct? Then what I'll do, I'll take component of force along the displacement, so it would be F cos theta, and then that multiplied by displacement, that is my work done, okay? On the other hand, okay, if I take this perpendicular here and take component of this S over here, I call this point D, this point, okay? What is OD? OD is S cos theta. So S cos theta multiplied by F, that is again equal to W, correct? So if you see these two, work done, see, work done is F cos theta into S or S cos theta into F. Is it not the same thing? It is going to give you the same thing, right? Because theta is some angle, some fixed angle. It can be 30 degree, it can be 45 degree, it can be 60 degree, it can be 10 degree or 5 degree, anything, okay? But cosine of that angle which you are referring to, it is going to remain constant, correct? Again, the magnitude of force and displacement, that is also going to remain constant. So my work done is equal to, so if I take this, it would be F bar dot S bar, and if you take this, it would be S bar dot F bar, correct? So it clearly shows that F bar dot S bar is equal to S bar dot F bar is equal to F into S into cos theta. So that was about our scalar product definition and how it really works. Okay, in the next video we'll do little more details about scalar product. Thank you.